Hi, 2. We're here to discuss a proof of the Pythagorean Theorem. What's a proof? Maybe this can help. Anyway, it's more of a demonstration of why the Pythagorean Theorem works. If you want to go through the proof with me, just prepare the following materials. A rectangular piece of paper, any rectangular piece of paper, scissors, and some markers. Okay? Are you ready? Here we go. Okay, so I actually have pre-cut some triangles here, but for the sake of you trying to follow this proof and trying to do it yourself, we start with a rectangular paper. What's the first thing that you do? You cut the paper in half. You cut the paper in half just like this. So if this was your rectangular paper, you're going to cut it in half. So you basically end up with two rectangles. Okay? Actually, it doesn't matter if you cut it crosswise or lengthwise. Maybe you could try lengthwise. So mine's cut crosswise. That'll do. Okay? So after you cut it in half, you cut each of these two resulting rectangles through the diagonal. Okay? So once you cut up this rectangle, you'll actually have two right triangles. Once you cut up this rectangle, you'll actually have another two rectangles. So you basically end up with what? With four congruent right triangles. Right? You got that? Okay. Okay, now let's talk about one right triangle, which is basically the same as all of these right triangles that we have here. Okay? So we have this, it's a right triangle. Again, just to review, the Pythagorean Theorem only works for right triangles. So for the sake of this proof, let's call this side A, this side B, and the length of the hypotenuse to be C. Okay? So we have a right triangle whose legs are A units long, B units long, and C units long. Okay? So after that, we try to go back to this. Okay? Once we go back to these two rectangles, comparing it to the triangle that we have here, this would be A units, this would be also A units, this would be B, this would be B, okay, and all the way around there. You guys agree with that? Yeah, I think that's about correct, right? Okay, so let's talk about the area of one rectangle. What's the area of a rectangle? The area of a rectangle is length times width. Length times width. So this is basically B units long and A units wide. So length times width would be B times A. Would you guys agree? So the area of this rectangle is B times A, which is actually the same as AB. Right? So that's length times width AB. But since we have two rectangles, okay, the area of this is also AB. Right? What if we go back and talk about the total area of that whole piece of paper? What if we go back and talk about the total area of all of these four right triangles? Would you guys agree that if we put these two together, okay, the total area is equal to AB plus AB, or simply put, 2AB. Okay? So the total area for these four right triangles would be 2AB. I hope that's clear. Now we go on to the real proof. Okay, to continue, I'm going to work with an identical set of figures right here. So these are exactly the same as these rectangles. So this would also be A, this would also be B, this would also be A, this would also be B. Okay? And watch very carefully as I try to rearrange this in a certain manner. Watch where the actual lengths would go. Okay. So notice that I actually formed another big square, or a big square. Okay? Now let's try to look at this square and try to see the lengths or the dimensions of the square. If you were looking very closely, you would have remembered that this is still A, this is still B, this is still A, this would have still been B, still A, still B, still A, and still B. Okay? So those are the appropriate lengths of each of those legs of the rectangles. Okay? So, now we talk about the area of this big square. How do we get the area of a square? The area of a big square, of a square, is basically side times side, right? But how long is one side of the square? We could actually express it as A plus B, right? Since we're trying to get the area, we're going to have to multiply side times side, or in this case, A plus B times A plus B. Okay? Now we continue. If we go back to each of these triangles, the hypotenuses would actually be C. And notice that there's a hollow part in our big square. The hollow part of our big square is another square whose side is C. Right? So we could now talk about the hollow part, or the small square, or the smaller square, I guess. And what would be the area of this smaller square? It's also side times side. But in this case, each side is C units long. So it's going to be C times C. Okay? There you go. Okay? Let's do a bit of algebra on each of these areas. Okay? So A plus B and A plus B. If you do your algebra here, or if you remember the shortcuts you learned in High 1, it will become A squared plus 2AB plus B squared. Okay? Maybe you could pause and try to review your multiplying algebraic expressions from High 1. And C times C could simply be talked about as C squared. Right? Okay. Now, why did I put these two expressions, the area for the big square and the area for the hollow square or hollow part, side by side? Because the next thing I want to do is talk about the areas of the colored parts. I just want to talk about the area of this colored part. Okay? Wouldn't you agree with me that the area of those colored parts would simply be the area of the big square minus this hollow square right here? I hope you agree with me. Okay? So it's actually going to be the area of the big square minus the area of the hollow part. We're talking about the areas of the orange colored parts here. So it would have been this minus this, or this minus this. So if we're going to talk about the area of the colored parts, it's just going to be A squared plus 2AB plus B squared minus C squared. That's it. Wait a minute. Aren't these colored parts the same as what we talked about earlier? It is, right? Okay. So get ready for a bit more algebra. Here we go. The total area for all of these four triangles was 2AB. We talked about that earlier. So it should be the same as the area of what we talked about as the colored part of this figure. So this must be equal to 2AB. Okay? And with that, all we need to do is a bit more algebra. Okay? We have this equation right here. Okay? And if you notice, if we subtract both sides by 2AB, what you'll end up is a squared plus b squared minus c squared equals 0. Right? Because these two will cancel out, these two will cancel out, so you end up with that. Just a little bit more algebra. If you add c squared to both sides, what do you end up with? You're actually going to end up with a squared plus b squared equals c squared. And lo and behold, that's your Pythagorean theorem. So hopefully with this demonstration, we have explained or we have provided one proof of the Pythagorean theorem. Thank you very much, I do.